Salam sejahtera everyone. We are from Group 11, Section 1. So today we are going to present the flash calculation for separating mixture for acetone and chloroform. Once again, we are from Group 11, Section 1. Hi everyone. So this is our group member. It consists of three members, which is me, Yong, Ivy, and GJ.
Now, I'm going to introduce you to the concept of flash distillation, a fundamental process in chemical and petrochemical industries. Let's begin with an overview of what flash distillation is. As you can see from the diagram, flash distillation is a single-stage separation process. It starts with the liquid mixture being fed into a system via a pump. This mixture is then heated in a heater. The essence of flash distillation is to partially vaporize this liquid mixture by either reducing its pressure or increasing its temperature. This change causes the more volatile components to vaporize, while the less volatile components remain in the liquid state. This process leverages the differing volatilities of the components in the mixture, making it an efficient method for separating and purifying substances. In summary, flash distillation is a crucial technique used to achieve efficient separation of liquid mixtures based on their volatilities. In the following slide, we will delve deeper into the mechanisms, applications, and advantages of this process.
Hi, I'm CJ. Now I will expand on the principle of operation of flash distillation. The principle of flash distillation relies on the equilibrium between liquid and vapor phase. Where a liquid mixture is subjected to a sudden change in pressure of temperature, it partially vaporizes. The resulting vapor and liquid phase have different compositions because the more volatile component tends to concentrate in the vapor phase, while the less volatile component remains in the liquid phase. There are also some significance in industrial applications. Flash distillation is widely used due to its simplicity and effectiveness in separating components with significant difference in volatility. It requires minimal equipment, typically a flash drum or a separator, and it is often used as a preliminary step in more complex separation process. For example, it can be used in crude oil refining, desalinating ocean water, and capable of separating ethane from octane.
So the binary mixture of acetone and chloroform are commonly solvent in different boiling points, making them ideal candidates for separating through flash distillation. Acetone has a lower boiling point, which is 56 degrees Celsius, compared to the chloroform, which is 61 degrees Celsius, which means that acetone is more volatile and will preferentially vaporize during the process. To understand the importance of the application of flash distillation of acetone and chloroform is crucial in various industrial processes, including solvent recovery in chemical manufacturing, purification processes in pharmaceutical industry, and production of high purity chemicals. So the objective of this project is to design a flash for separating a binary mixture of acetone and chloroform.
So let's move on to the process and composition conditions. The overall composition of the mixture consists of acetone, 0.5 mol per mole, and chloroform, 0.5 mol per mole. This equimolar mixture provides a straightforward example to demonstrate the principles of flash distillation. Next, we need to consider the operational temperature. The temperature data for the substance are the boiling point of acetone, which is 329.4 Kelvin, and boiling point of chlorine, 334.3 Kelvin. So the average temperature is 331.85 Kelvin, which corresponds to 58.7 degrees Celsius. The operational temperature for our process is 330.15 Kelvin, which corresponds to 57 degrees Celsius. This temperature is chosen to ensure effective separation by taking advantage of the volatility difference between acetone and chloroform. Now, we will move on to the key assumptions and basis for our flash distillation process. Firstly, we have a set of assumptions to simplify our analysis. The acetone and chloroform mixture is considered an ideal solution. This implies that Rose's law is applicable, meaning the partial pressure of each component is directly proportional to its mole fraction in the mixture. We assume ideal gas behavior in the vapor phase. This means that the vapor mixture adheres to the ideal gas law, which simplify calculations related to pressure, volume, and temperature. Next, the process operates under steady-state conditions. This assumption indicates that the flow rate, temperature, and composition do not change with time, ensuring a consistent operation. Finally, we assume that the flash separation operates with 100% efficiency. This implies that the separation perfectly distinguishes between the components based on their volatilities without any losses or imperfections. For our basis, we consider a mole mixture fate.
Now I will introduce the entering equations which can help us to calculate the saturation pressure. The equation is ln P set equal to A minus B over temperature in degrees Celsius plus C. There are three parameters which are A, B, C for entering equations. We can refer to Appendix B, Table B2 in textbook to find the parameters regarding the different components. For acetone, we can find the ABC and we insert into the equations, we can guess the P saturation is 104.1246 kPa. And for chloroforms, after we get the parameters and inserting to the equations, we can get the P saturation is 88.4839 kPa. After calculated the P saturation for acetone and chloroform, we will now determine the different pressure, which are bubble pressure, dew pressures, and the operating pressure. For all the compositions used in calculating the different pressure, x1, x2, y1, and y2, we will refer the overall composition we assumed before, which are 0.5 for acetone, 0.5 for chloroform. For bubble pressures, the equation is x1 P saturation 1 plus x2 P saturation 2. After we insert the data, we will get the bubble pressure is 96.3043 kPa. And for dew pressure, the equation is 1 over y1 per P saturation 1 plus y2 per P saturation 2. And after we insert the data, we will get the dew pressure is 95.6692 kPa. And for the operating pressures, must be in range of P bubble and P dew. So we determine the operating pressure is 96 kPa.
Now I will present about the flash calculation. Since the operating pressure is in between the bulb pressure and dew pressure, so the system is axis in two-phase region, a flash calculation is possible. Thus, from the Rock's law, we can calculate that Ki equals to Yi over Xi. So K1 is equal to 1.0846, while K2 is equal to 0.9217. The xi which is the liquid form can be calculated by arranging the Rock's law. So the xi is equal to the x1 is equal to p minus p1 set over p2 set over p1 minus p1 set. So the x1 is equal to 0.4805, while x2 is equal to 0.15195. On the other hand, yi can also be calculated by using arranged Rock's law, which is y equals to xi ki. So y1 is equal to 0.5212 and y2 is equal to 0.4788. Next, we will calculate the mole of vapor by using the formula yi equals to zi ki over 1 plus v ki minus 1, which is equal to 1. So by using the trial and error, we can get that the moles of vapor is equal to 0.47833, which is in the calculation of trial and error, we can get the summation of y is equal to 1.
Now I will move on to the calculations of moles of vapor and the moles of liquid in the system. So for the moles of vapor, the formula used is summation of Zk over 1 plus V bracket K minus 1 equals to 1. So by substituting the value based on our example and solving this equation, you will get V equals to 0.4783 mole. Next, to find the moles of liquid, we will use the formula L equals to Y minus V. So by substituting the value of V, we get L equals to 0.5217 mole. So in summary, the moles of vapor in the systems are 0.4783 mole and the moles of liquid are 0.5217 mole. And so that is all from us. Thank you for listening.